Okay, so I'll talk about subconvexity for GL3 cross GL12 functions in the GL3 spectral aspect. So let me begin by quickly recalling the subconvexity problem. So for a mass form F on the group SLDZ, we have the standard L function of Godema-Jacquet given by sum over n from 1 to infinity lambda fn by n power s, which converges absolutely for real part of s greater than 1. Here lambda fn denotes this particular Fourier coefficient in the Fourier-Wittiger expansion of f. This L function can be shown to satisfy the Riemann type functional equation relating its values between s and 1 minus s. Lambda fs is the completed L function which contains the power of the conductor of f, a power of pi, and product of this d many gamma factors, each containing the spectral parameters. So this from the functional equation, we have the complete picture for these L functions in the region real part of s greater than 1, union real part of s less than 0. And the region in between, which is real part of s is from less than 0 and greater than less than 1 and greater than 0 remains elusive. However, the Phragmen-Lindelof convexity principle, which is a result in complex analysis, gives us some upper bounds in at any point inside this critical strip in terms of bounds in terms of the size in the boundary lines. So if you define the analytic conductor to be the product of QF times the product of this product of all the parameters appearing in the gamma factor, then this principle, the convexity principle, will say that the central value at height t will be bounded by this analytic conductor for 1/4. Now a subconvexity bound is any bound breaking the convexity barrier by some positive power delta. So one usually seeks convexity when one of the parameters are varying. So for example, if t is varying and everything else is fixed, it is called the t aspect subconvexity. When the level is varying, it is called the level aspect, and when the kappa i's are varying, it is called the spectral aspect subconvexity. So there are three standard approaches through which the subconvexity problem can be attacked. The first is the classical moment method. The second is the delta method initiated by Munshi, and the third is the period integral approach initiated by Michel and Venkatesh. So in this talk, I'll be talking about the first approach, which is the moment method. So let me now briefly outline the philosophy behind it. So if pi naught is our automorphic form which we are interested in, then since averages are expected to behave much more nicer than the individual terms, we embed this pi naught in a family and consider this second moment instead, where the sum is over a spectrally complete family containing pi naught. So now if one can deduce nice enough bound for S using, for example, say the trace formulas, then dropping all the terms but pi equals to pi naught, we arrive at a bound for our central L value, which will be the square root of S. So, but how does one choose this family F to get a nice enough bound? So one way is to use the approximate functional equation. So if q pi denotes the conductor of pi, then the approximate function equation gives us the following finite sum approximation of the central L value, where now the sum runs up to square root of the conductor into lambda pi n by n half, which is roughly this c pi power minus 1/4 into this finite sum going up to the square root of the conductor. So if you substitute this finite approximation in our initial average S, then this will become c pi naught power 1 by half sum over your spectrally complete family F into absolute value square of this finite sum. So now if you open the absolute value square and apply a suitable trace formula, you can see the diagonal will be roughly of size of the length of this n sum, which is square root of the conductor, into the size of the family, into this factor, which will equal to just the size of the family. So to beat the convexity, you can now see that you need to choose your family F to be little less than the square root of the conductor. And for the off diagonal to be acceptable, one usually needs the family to be big enough. So this restriction will put a severe restriction. This condition will put a severe restriction in your family F, but it turns out that such a family exists for GLC or automorphic forms, which is what I'll be talking about. So before going on to the family, let me briefly highlight some of the existing subconvexity bound in the GL3 world and their and the methods used to obtain those. So the first breakthrough was obtained by Xiaoqin Li, in which for self-dual SL3Z Hecke mass form pi, she considered the first moment average of LS pi to state with SL2Z forms, and was able to reduce the following two subconvexity bound. The first is the subconvexity in the T aspect with a saving of 1 by 16 over the convexity bound. And the second is the subconvexity for GL3 cross GL2 in the GL2 weight aspect with a saving of 1 by 8 over the convexity bound. Her proof crucially used the non-negativity of this central L value, which followed from the self-duality assumption. Following a similar approach, Valentin Blumer in 2012 proved the following subconvexity for GL3 cross GL2 twisted by Dirichlet character with modulus Q with a saving of 1 by 4 over the convexity bound. Here again, pi was assumed to be self-dual, and furthermore, chi is assumed to be a quadratic character modulo Q. So new ideas were required to handle the more general class of GL3L functions. So in his series of paper, Munshi introduced his very versatile delta symbol approach, through which among other important results, he established the following two. The first is the first is the subconvexity bound for GL3 in the T aspect with a saving of 1 by 16 over the subconvexity over the convexity bound. Here pi is now you can take pi to be any SL3Z Hecke mass form, and the second one is subconvexity for GL3 twist with Dirichlet character chi of modulus Q with a saving of this exponent. Here again, pi is allowed to be any SL3Z Hecke mass form, and chi is any Dirichlet character modulo Q, non-trivial Dirichlet character modulo Q. So, so recently he was also able to establish the subconvexity for GL3 cross GL2 in the T aspect with a saving of 1 by 51 over the convexity bound. Here again, pi is any general SL3Z Hecke mass form, and F can be any SL2Z form, holomorphic or mass. Kumar Mallesam and Singh were able to adapt the delta symbol approach to treat the subconvexity for GL3 cross GL2 in the GL3 spectral aspect with a saving of 1196 over the convexity bound, where so this bound so the spectral parameter here is the spectral parameters are such that the distance are bounded by the 2/3 of the norm of the Langlands parameter. In the same paper, they were also able to establish subconvexity for GL3 cross GL2 in the GL3 spectral in the generic case as well, whereby generic I mean that now the difference can all the spectral parameters and their difference are of the same size. But this they needed to assume some condition on the GL3 coefficients at primes. And they were also able to establish a conductor dropping case assuming the same condition on the GL3 coefficients. So all these results use the help of GL1 and GL2 harmonic summing from the circle method and the Petterson trace formula, further enhanced by the Voronoi summation formula. So using subconvexity using GL3 harmonics were first obtained by Blomer-Butkin, where they used the GL3 spectral theory to evaluate an amplified fourth moment of GL3 forms, and were able to deduce the following subconvexity bound in the GL3 spectral aspect with a saving of roughly 10⁻⁻⁵ over the convexity bound. Here the Langlands parameter of pi is assumed to be in the generic position. I will define this what this means in a short while. So in this work, we take a step further and study second moment of GL3 cross GL2 L functions. So we fix f to be a holomorphic cusp form, or even the Eisenstein series Ez², and let pi naught be our preferred SL3G Heckemass cusp form with Langlands parameter in the generic position, by which I mean that each of the parameter and their differences are all of the same size, capital T. So by evaluating a second, so the associated ranking Hilbert function is defined as sum over R and n going from 1 to infinity, lambda pi naught R comma n lambda fn by nr square power s, which again converges absolutely for real part of s greater than 1. So this can again be shown to satisfy functional equation of the Riemann type and has a conductor of size T⁻⁶. So the convexity bound in this case will correspond to T⁻3/2. So we evaluate an amplified second moment of L½ of pi j twisted with the SL2G form F, and we're able to deduce the following subconvexity bound with a saving of 1/2022 over the convexity bound. And if you plug in your f to be the Einstein series, then note that this central L value will just be the square of L½ of pi naught. So, and hence as a corollary, we obtain the following improvement of Blomer-Butkin's result, where now the saving is roughly 10⁻⁻³ . So yeah, I'll now briefly sketch the proof. So we are interested in the second moment S, which is given by sum over absolute value square of L½ of pi j twisted with F, where the sum is over all GL3 forms pi j with Langlands parameter mu j inside a ball of radius 1 which centered around mu0. So in particular, this family will contain our form pi naught. So now, since the conductor of all the central L values in this family will be t power 6, the approximate functional equation will give us the following finite sum approximation, where now the sum is n going up to t cube lambda pi j 1 n lambda fn by n half, which is roughly equal to t power minus 3 by 2 sum over n going up to t cube lambda pi j 1 n into lambda fn. So if you use this finite sum approximation and substitute in your initial average edge S, then the sum S will look like this. And now you open the absolute value square, and you see the diagonal will be of size the length of the n sum, which is t cube, into the size of the family, which is again t cube by the Yeilds law, into this t power minus 3, which equals t cubed. Plus there will be an off diagonal part, which we expect it to be little less than t cubed. So this heuristic will says that S is roughly of size t cubed. So if you drop all but the term with pi equals to pi naught, then we can see that we recover the convexity bound, which is 3 by 2. So in such a scenario, to break the convexity barrier, we use the amplification method, in which we consider a amplified version of our initial average. So so for us, the amplification will look like this. So you choose a sequence of real numbers a pi j attached to each pi j, which for us will be roughly of the form sum over CL into lambda pi j 1 L, while L runs over primes of size capital L. Here CL are constant of absolute value 1, which is defined by this sine function. So this Cn is chosen in such a way that the amplifier at the value at pi naught is at least of size L. So then we can observe that our absolute value square of our central L value is bounded by this amplified average by L squared. So now if you open up this a pi j using this definition and push the lambda pi j 1L factor inside and combine it with the GL3 coefficient using the Ayyer relation, the sum becomes roughly of this form. And now you can see that the diagonal becomes t cubed into L plus the off diagonal will become t power 3 minus delta into some positive power of L. The point here is that the L variable is now nicely mixed with our initial harmonics in our sum S, which so that the diagonal will force will put some restriction on the L variable as well, and hence we can see as a whole you will gain a power of L in the a factor of L in the diagonal term at the cost of an increase in the off diagonal contribution by some positive power of L. So now if you choose your L appropriately, this will give us the subconvexity bound. So this is roughly how the amplification will work for us. So for the rest of the sketch, I will suppress the amplification part and only focus on proving the following asymptotic for our initial average S. So we want to show that this S equals a diagonal term which is roughly of size t cube plus a off diagonal term which is bit less than t cube. So now you open the absolute value square and push the spectral sum inside, you will arrive at this kind of sum, which is t power minus 3 sum over m comma n going up to t cube lambda f n bar into this spectral sum. So we are now in position to apply the GL3 Kronecker formula to the spectral sum mu j. So we use a version of we use the version developed by Butkin, which tells roughly the following. So the GL3 Kronecker formula is a certain orthogonality relation between this GL3 coefficient, which will transform the spectral sum to a geometric sum, which among other terms will involve SL3 Kloosterman sum and GL3 Bessel functions. So here this capital delta corresponds to the identity element in the while group. This sigma 6 corresponds to the long while element in the while group, and the sigma 4 and sigma 5 are the remaining contribution of the while group. And we need to add this Einstein contribution to make our family complete. So let us unpack the geometric side one by one. So the capital delta will detect m equals to n weighted by this factor, which is the spectral measure, which is roughly of size t cubed. The sigma 4 term will be this sum over the hyperclusterman sum as tilde weighted by this integral transform phi omega 4. And the sum runs over all d1, d2, satisfying this two conditions. So here, this phi omega 4 is a will oscillate like e power 1 by 3 and is negligibly small if y is less than t cubed. So for us, if you plug in the variables and work out this condition, this will imply that this d2 variable is at least of size n, so that this nm by d1 d2, which is less than nm by d2 square, since d2 is bigger than d1, will be less than nm by n squared, which is roughly of size 1, which is clearly less than the t cubed. And hence we see that this sigma 4 will contribute negligibly to our average, and we can ignore it. Sigma 5 is a similar looking term, which will again have no contribution to our average S due to similar reason as above. So the only interesting contribution comes from the long while element sigma 6. So so sigma 6 is sum over this long while Kloosterman sum divided by d1 d2 twisted by this phi omega 6, which you can think it of as the GL3 Bessel function. So so what are these long while Kloosterman sums? 1d1 or d2 co-prime, this is just a product of two classical Kloosterman sums. And when GCD of d1, d2 is greater than 1, it can be written as sum of such a product of two Kloosterman sums. And the sums will be parameterized by the factors of this GCD. So this is a recent result of Kiral and Nakasuji. This and for this phi omega 6 function, you can think so this will be the Archimedean analog of the long while Kloosterman sum, and can be written as an integral average of the product of two Bessel functions. So this representation is given in Blumer-Butkin's paper, and this will oscillate roughly like e power y1 half, y2 half, and will have trivial size t squared. So here by trivial size, I mean that I'm taking absolute values in this integral average over Bessel functions, and assuming no cancellation in this integral average. So this again is negligibly small unless both the parameters y1, y2 have some size given by this relation. So if you plug in the variables, our variables, then this condition will say that you can restrict the d1, d2 sum in sigma 6 going up to t. So with this information, let us calculate each of the contribution coming from the geometric side. So that diagonal contribution is very simple. It is just t cubed sum over m comma n going to t cubed lambda f n bar t cubed, which is the spectral measure, into delta of m minus n, which will be sum over m going to t cubed absolute value square of lambda fm, which is less than t cube, which is bounded by t cube. And this diagonal is the diagonal size is what we expected in our initial heuristic. So in the off diagonal side, off diagonal contribution, which we have shown only comes from the long while element, is e power minus 3 sum over d1 d2 going up to t 1 by d1 d2 sum over m comma n going to t cube into this GL2 coefficients times this product of two Kloosterman sums. Here I have assumed that d1 d2 are co-prime for simplicity, with twisted by this GL3 Bessel function. So recall that we need to show this off diagonal contribution to be a little less than t cubed. So now we will apply Voronoi summation formula to obtain cancellation in the GL2 sums. So there is a key observation here that the GL2 Voronoi summation formula will transform this Kloosterman sum into a Ramanujan sum. And in this way, we will save more than the usual square root cancellation in this sum. So if you apply the Voronoi summation formula to both the GL2 sum, you will roughly arrive at the following. So there will be a factor of t power 7 by d1 d2 sum over m tilde going up to t sum over n tilde going up to t, where now you have this congruent condition that you get from the Ramanujan sum into this integral average of your phi 6 phi w6 function times there will be product of two Bessel functions coming from the Voronoi summation formula. But since our GL2 forms are fixed, we can easily extract out the oscillation, after which the expression will look like this, which will be t cubed m tilde half x by d1 plus t power 3 by 2 and tilde half y by d2 integral over dx dy. So now if you trivially estimate at this stage, the first factor will be of size t power 5, since d1 and d2 is roughly of size t. So this will be t power 5 sum over n. Now notice that the m variable is getting determined by this congruent condition because t1 is size t and m also goes up to t. So this will be just 1. Similarly, for the n sum, 1 into t square, which is what we call the trivial size of this geometry Bessel function, into the square root cancellation from the x and the y integral. So the amplitude here is roughly of size t power 3 by 2 into m tilde half. So this will be t cubed by d1, which is sorry, this will be t squared, t power 3 by 2 into t half t squared by t. So this amplitude is of size t. So we expect this square root cancellation in both of this x and y integral. So this will evaluate to be t power 6. So if you plug in this estimate, your off diagonal contribution will be t power minus 3 into t power 6, which will be t cubed. So here we have arrived at the boundary of our required estimate. So we need to save something more in this dual sum. But now you can see that there is nothing left in the m and the n sum, and the only possibility is obtaining some cancellation, obtaining some non-trivial estimate in this Fourier transform of our GL3 Bessel function. So that's what we do next. So we need to trivially estimate this Fourier transform of our GL3 Bessel function. So here note the trivial size is t squared, which comes from the size of this, times the square root cancellation from the x and y integral. So this will be just t. So a non-trivial estimate amounts to showing some cancellation inside this integral average of the phi omega 6 function. So let me make this precise. So when theta 1 is of size theta 2, things are nice, and you can you have the following integral representation of your GL3 Bessel function, which is given as t cubed into this oscillatory factor x by 1 it2 into this integral u integral over the product of these two k Bessel functions times this u power 3 i2 du by u. So now you can see that a non-trivial estimate for this integral I amounts to showing some cancellation inside this u integral, which we were ignoring earlier. Here T2 is just imaginary part of mu2, and T3 is the imaginary part of mu3 minus mu1, which both of which are of size t by our assumption. So now if you plug in this representation in your integral I, you will arrive at the following x and y integral, which will be roughly of the form IU alpha given by this integral. So so the trivial bound here is just absolutely bounding this k Bessel function, which is of size 1 by root t. Yeah, no, okay. So yeah, so our goal is to now obtain trivial estimate for this integral transform, where T1 and T2 are of size capital T, and alpha and u we can think to be also of size capital T. So one way to so one way to proceed is to obtain use the already known asymptotics for this k Bessel function. And then use this, and then finally execute the x integral and use this asymptotic to our initial integral I, and finally execute the u integral to obtain some cancellation. So, however, we do not use the approximation of the k Bessel function since, as we know, this k Bessel function behaves very differently near the transition range alpha x equals to t1. So instead, we use the we keep the k Bessel function as it is and use the integral representation and execute the x integral first. So the x integral will have no transition range and can be evaluated by standard stationary phase argument. So after you evaluate the x integral, your final integral, the transition range for your final integral will be then shifted to this particular point. Pi u by alpha is t1 plus t2 by t1 minus t2, which is roughly of size 1 by our initial assumption. So you have to treat this integral I differently in this transition range. So I will not discuss that. So away from this transition range, you will have a nice asymptotic for your integral transform I alpha, which will be roughly fu alpha by t into this e power t into this phase function phi u alpha. Here phi u alpha will be a mildly oscillating smooth wave function. Here the factor t comes from the size of the Bessel function. So the size of the Bessel function is square root t, and you have a square root cancellation in the x integral, from which you will obtain 1 by square root t. So the size of so the size of this integral will be size t, which is reflected in this denominator. So once you have this nice asymptotic, you can substitute in your initial you can substitute in this x and y integral. After which you will arrive at the following u integral, which will be hu times e power t phi u du, where hu is the product of two weight function that you get from your estimate asymptotic of this I alpha. So you have this weight function coming from the u variable, and this asymptotic coming from the v variable. The weight function coming from the u variable and the weight function coming from the v variable. And the phase function is just the sum of the two phase function. So this phi u is what you got from your approximation in the u variable, plus this phi v that you got using the v variable, plus this initial oscillation which was present in the u integral. So what we know about this phi u phase function is the following. We know that the derivative is roughly pu by fu, where pu is a degree 13 polynomial in u, and fu is a smooth function of size roughly 1. So this is the first information you know. The second is the j derivative of phi u is bounded by this a power j, and the j derivative of hu is bounded by b power j, where a and b are not too large. So these two data will allow us to say that this integral will be negligibly small when this u are away from the roots of the polynomial p. So which, in other words, this is negligibly small unless u is very close to one of the roots. So just trivially estimating this integral near the roots, you will we get the non-trivial bound t power 1 minus delta, which for us delta comes out to be 1 by 140. So this is the non-trivial. This is we have achieved our goal for the case when theta 1 and theta 2 are roughly of the same size. When they are not of the same size, in other words, when the d1 and d2 variable are unbalanced, the saving from the Ramanujan sums will become ineffective. So in this case, we will need to gain more in the analytic part. So a more careful treatment will actually yield that this integral is bounded by 1/6 power of this ratio, minimum of this ratio, into t power 1 minus delta. So, so now this saving will balance the loss in the Ramanujan sum when d1 and d2 are unbalanced. So yeah, so this is the brief sketch of the proof, and I'll end my talk with saying that these GL3 harmonics phi omega 4y, phi omega 6 by 1 y2 deserves further study. For us, the spectral parameters mu naught are essentially fixed throughout the whole calculation, and we have required very little from them. And even with that, we arrive at a subconvexity bound. So for example, one wonders what is the nature of the spectral oscillation in this in the geometric side, and how does the geometric side changes when the test function in the spectral size also oscillates with respect to the spectral parameter. So this kind of one might need to address this kind of questions while trying to use this harmonics to address some different family of L functions. Yeah, so that's it. Thank you.